You've heard of a tangent line, but have you heard of a tangent quadratic? In this video, I'm going to show you how to compute the best fit parabola to the graph of a function. So to start out, let's do an example. I want to work with, say, y equals 1 over x. And one problem that you might see in a calculus textbook, a problem that I could ask, is pick the points x equals 1, y equals 1, and find me the tangent line to the graph of y equals 1 over x through that point, 1, 1. And the way you'd do that, you'd say maybe y equals f of x. And then you'd say, OK, let me calculate f prime of x. And you could do this with the power rule or the quotient rule. Either way, you'll end up with minus 1 over x squared as your answer. And just because I'm going to use it in a little bit, let me also calculate the second derivative. That second derivative, again, by the power rule or by using the quotient rule, when you calculate this out, you're going to get 2 over x cubed. Now, if you want to find that line tangent to 1 over x at the point 1, 1, then you're going to use that point slope formula. You've got your point 1, 1. You've got your slope, that's f prime of 1. So you're just plugging in the number 1 into this formula, and negative 1 will be your answer. So your tangent line, I'll call it t for tangent, it's going to have slope negative 1. It's going to be passing through the point 1 and the y value 1. So that's the formula for the line tangent to 1 over x at the point 1, 1. In fact, here's the graph of 1 over x, and here's that tangent line going along with it. But suppose we wanted to do something different. Suppose we wanted to find not just the tangent line, that is to say, the line that goes through the point 1, 1 and best approximates the function. Say we wanted to find the best fit parabola, the best fit quadratic function that goes through the point 1, 1 and is also closest to the function. And the first question to answer that is I have to tell you even what it means for the quadratic function to have like the best fit. And in order to explain that, I want to re-explain how do you find the tangent line from another perspective. So another way to find this formula for the tangent line t would be to do the following. It would be to say, well, look, generally speaking, the equation for a line is going to be some constant times x minus 1 plus another constant. I call the constants a and b. And I just write x minus 1 because I know I'm going to center it at the point 1. And how do I find those points? So I could make the requirement that the derivative of the line at the point 1, so I'll go ahead and plug in a 1 there, is equal to the derivative of the function at the point 1. But when I take the derivative of t of x, what I get is the constant b goes to 0, and I'm just left with constant a. And so when I plug in 1, I'm just left with constant a. And so when you put that together, that tells me that a has to be equal to f prime of 1, which in this case is equal to negative 1. And we already figured that out from before. And suppose I also wanted to know that not just the derivative, but when I plug in the number 1, I actually also get f of 1. If you plug in the number 1 here, 1 minus 1 is 0, you're just going to be left with b. And so that's telling you that b is equal to 1. So one way to find that tangent line is sort of to just write this general form, and then requiring that t of 1 equals f of 1, and t prime of 1 equals f prime of 1. That's another way of saying that it has to be the line that best approximates the function near the point 1, 1, because the value of the function and its first derivative match that function. That's sort of the magic or the point of tangent lines. So if I want to do this with a tangent quadratic, I'm going to have to start with a general quadratic function. And so what's that going to be? I'm just going to look at a constant times x minus 1 squared plus another constant times x minus 1 plus another constant. So that's a typical quadratic function, second degree polynomial, but centered at x equals 1. And so I can say the conditions that I want for this to be the best fit quadratic are simply going to be that if I plug in 1, I'm going to get f of 1. That if I take the derivative and plug in 1, I'm going to get f prime of 1. If I take that second derivative and plug in 1, I'm going to get f double prime of 1. And so how can I figure out what's what? Well, I know that f of 1 is equal to 1. I know that f prime of 1 is equal to negative 1. And plugging in the number 1 here, I can see that f double prime of 1 is just going to be equal to 2. So how does that correspond to the coefficients? Well, if I plug in 1 for x, I'm going to get 0, I'm going to get 0, I'm just going to get c. So that tells me that c has to be f of 1, has to be equal to 1. Now if I take the derivative of q of x, that's going to give me, well, the power rule is going to bring down this exponent. It's going to give me 2 times a times x minus 1. And then it's going to give me b times 1. That's because I get derivative of x is 1 and derivative of negative 1 is 0. Just left with the constant b. Constant c goes to 0 when I take the derivative. So when I plug in 1, I'm just going to be left with b. So that tells me, like before, that constant b has to be equal to negative 1, the slope of the tangent line. And for the second derivative, I take the derivative of q prime, and this constant b now goes to 0, and the derivative of 2a times x minus 1, that's equal to 2a. So 2 times a has to be equal to f double prime of 1, and so that's going to tell me that a has to be f double prime of 1, but actually I have to divide it by 2 because of this extra factor there. So f double prime of 1, that's equal to 2, so 2 over 2, that's equal to 1. So let's just plug all that in. So now my tangent quadratic, q of x, that's going to be equal to 1 times x minus 1 squared plus b is equal to negative 1. So it's really, I'll just write minus instead of plus and negative. So minus x minus 1. And then plus c with c equal to 1. So that's supposed to be the quadratic function that best approximates our function. And let me come over here and let me now show you that quadratic function plotted against 1 over x. And you can see that it sneaks right up through and it gives a great approximation.